Hi, I'm Hayden,
And I'm Naman.
and this is our Matter and Change video project.
If you want to skip ahead to the cool parts, here's some timestamps for you. If not, let's get started. Our first chemical reaction is going to be burning hydrogen gas. Since we don't have hydrogen readily available, we have to produce it with another reaction. Our plan is to drop some aluminum into hydrochloric acid.
Hydrochloric acid is a clear, colorless substance with a density of 1.20 grams per milliliter and a melting point of negative 27.67 degrees Celsius. It has covalent bonds with the hydrogen and oxygen bonding on 2 electrons, is very stable and lasts very long without degrading. Hydrochloric acid is not flammable, but it does react with most metals, releasing hydrogen, and can also produce deadly chlorine gas. The production of hydrogen is precisely why we're using it for this experiment. Hydrochloric acid is also very corrosive and highly toxic. Its percent composition is 97.03% chlorine and 2.97% hydrogen, with a molar mass of 36.46 grams per mole. Fun fact, despite being highly toxic and corrosive, hydrochloric acid is present in our stomachs. The thick layer of mucus lining our stomachs is what prevents us from being eaten inside out.
Aluminum foil is covered with a thin layer of aluminum oxide, which, when exposed to hydrochloric acid, produces aluminum chloride and water vapor. This exposes the aluminum underneath, which can then react with the acid, which will produce more aluminum chloride and, more importantly, hydrogen gas. We will inflate a balloon with the hydrogen and then light it on fire. This will cause an oxidation reaction where the hydrogen will combine with oxygen in the air to form water. It'll also form a lot of fire and an explosion. Let's begin. Reaction takes place when the components of the reactants are shuffled around so that the chemical identity of the reactants is changed. We know the hydrogen gas being burned was a chemical reaction because when anything burns, it's an oxidation reaction, which is a chemical reaction.
Let's look at column 5A of the periodic table. Here we find bismuth, which is a post-transition metal with atomic number 83. Bismuth has 41 known isotopes, only one of which is actually stable. It has an atomic mass of 208.980 atomic mass units and thus a molar mass of 208.980 grams per mole. Bismuth is a very brittle metal, as you can see in the bottom right corner. Bismuth naturally occurs in compounds with oxygen, sulfur, and carbon. It's pretty chemically stable and reacts with a decent number of elements. Bismuth is not flammable but can still be burned, and when burned produces a blue flame. Bismuth has relatively mid-level reactivity and reacts to some acids but not hydrochloric acid. It's non-toxic but slightly radioactive and safe enough for human handling. Bismuth is a grayish-white metal with a reddish tinge and melts at 271.3 degrees Celsius. It has a density of 9.747 grams per milliliter at 20 degrees Celsius. Additionally, it has 83 protons, 83 neutrons, and 126 electrons, with 5 of them being valence electrons.
When cooled down slowly, bismuth forms geometric rectangular crystals, as seen in the pictures in the middle. For our first physical change, we're going to melt bismuth. We're going to take a few chunks of bismuth and then put it inside a pot, and then heat it up using a torch and a Bunsen burner. This will cause the bismuth to become a silvery liquid. Our second physical change is going to be freezing or crystallizing bismuth. We're going to slowly cool down the liquid bismuth until it becomes a solid again and forms those nice rectangular crystals we mentioned earlier. Let's begin.
Physical changes were physical changes because they didn't actually change the chemical identity of the substances. For example, the melting and crystallizing of bismuth was a physical change because it only changed the state of matter of the bismuth, not the chemical identity. There was no evidence of any new substances being created, like gas or color changes, which are both indicators of chemical changes.
Our second chemical reaction is going to be the burning of gunpowder. To make gunpowder, we need to combine carbon, potassium nitrate, and sulfur. Carbon is an element that can be found in column 4A of the periodic table. It is a nonmetal and has an atomic number of 6 and an average atomic mass of 12.011 atomic mass units. It has 3 naturally occurring isotopes. Carbon has 6 protons, 6 neutrons, 6 electrons, and 4 valence electrons. It has a molar mass of 12.011 grams per mole. The carbon we bought was in the form of charcoal, which is an allotrope of carbon known as amorphous carbon. We bought it at Ace Hardware, and we crushed it up for our reaction. Carbon can form many covalent bonds with other elements and other carbon atoms, which is why it has so many allotropes. It can bond indefinitely with itself, and has extremely strong bonds, which is why it's present in all life. Carbon is quite chemically stable, although it can bond with many other elements and itself over and over again. It's not really flammable, although it can be burned when in substances like charcoal. Despite being stable, carbon reacts with many other elements, especially oxygen. It's not very toxic, although large amounts being inhaled can cause lung and heart damage. Carbon has a melting point of 3,550 degrees Celsius and has different densities based on its allotropes. The allotrope we're using, amorphous carbon, has a density of 1.9 grams per milliliter. Carbon is generally gray or black in most allotropes.
Now we'll talk about potassium nitrate, which is a compound. Potassium nitrate has a percent composition by mass of 38.6% potassium, 13.9% nitrogen, and 47.5% oxygen, with a total molar mass of 101.10 grams per mole. Potassium nitrate is an ionic compound and is relatively stable, only degrading at high temperatures. Potassium nitrate is non-combustible but will accelerate fires. It gives off fumes when combined with acid and is a strong oxidizer. Potassium nitrate also gives off toxic nitrogen oxide fumes when combined with acid. Potassium nitrate has a white color and melts at 333.44 degrees Celsius. It has a density of 2.11 grams per milliliter.
Finally, let's talk about sulfur. Sulfur is found in column 6A of the periodic table and is a nonmetal. It has atomic number 16 and 41 known isotopes. It has an atomic mass of 32.066 atomic mass units and a molar mass of 32.066 grams per mole. It has 16 protons, 16 neutrons, and 16 electrons, with 6 of them being valence electrons. Sulfur forms sulfides with all metals except gold and platinum, and forms compounds with some nonmetals too. It's chemically stable below 96 degrees Celsius. Powdered sulfur is highly flammable and can be used to make gunpowder, as you can see in the video in the middle. It was formerly known as brimstone, which means burning rock. Sulfur has 6 valence electrons, which means it only needs 2 to have an octet, so it has relatively high reactivity. Sulfur has low toxicity, although it's irritating to the eyes, and inhaling or ingesting large amounts can cause high discomfort. Burning sulfur also produces sulfur dioxide, which is very unhealthy to inhale. As for physical properties, sulfur is a bright yellow color and has a density of 2.07 grams per milliliter at 20 degrees Celsius. Sulfur has a melting point of 112.8 degrees Celsius or 235 degrees Fahrenheit. We bought our sulfur in powdered form, as you can see on the right, and we got it from Ace Hardware in the gardening section in case you want to make gunpowder yourself at home. Now on to the actual procedure. We're going to mix carbon, potassium nitrate, and sulfur in this ratio to form the gunpowder mixture. When we light it on fire, it's going to produce these 3 compounds. The K2S, or potassium sulfide, will be visible on the ground where the gunpowder is burnt, in the form of a powdery residue. The nitrogen and the carbon dioxide will be visible in the fumes that come out of the gunpowder while it's burning.
Good evening, ladies and gentlemen. At this time, we'd like to call to your attention the importance of illustrating
this is a chemical reaction for several reasons. First of all, it is burning, which is an oxidation reaction. We found a new substance on the ground, which was potassium sulfide, which indicated that a chemical reaction had taken place. There was also gas released in the form of nitrogen and carbon dioxide, which was further evidence to a chemical reaction having taken place. All the cool stuff is over now, but we still have a few more things we need to do to meet the requirements, so here we go. There are 4 different classifications of matter, and they are
elements, compounds, homogeneous mixtures, and heterogeneous mixtures.
We already talked about all of our elements and 2 of our compounds, so now let's talk about our remaining compound and our mixtures.
Hydrogen peroxide, or H2O2, is a compound that is 94.07% oxygen and 5.93% hydrogen. It has a molar mass of 34.01 grams per mole and has covalent bonds, is very stable, degrades into oxygen and water, and is non-combustible, although it is a fire accelerant. Hydrogen peroxide decomposes when exposed to light and when it is exposed to organic/reactive compounds. It causes irritation at the site of contact and is not very toxic as it degrades in the human body. Hydrogen peroxide has a melting point of negative 0.43 degrees Celsius, a density of 1.45 grams per milliliter, and is colorless.
The video on the right is of my contact lens cleaning system. The clear liquid is hydrogen peroxide, which is disinfecting the contact lenses and simultaneously decomposing into water and oxygen bubbles. Now let's talk about our mixtures. As you can tell, we kind of ran out of time on this section. Our first homogeneous mixture is gunpowder, which is 75% potassium nitrate, 15% carbon, and 10% sulfur. Our second mixture is hydrogen gas and water vapor inside a balloon, which is produced from our hydrogen and aluminum reaction. Our third homogeneous mixture is nitrile gloves. The nitrile gloves are made of a mixture of nitrile and antioxidants and coagulants.
All 3 mixtures are homogeneous mixtures because all of the components are evenly dispersed and uniform.
Now on to our heterogeneous mixtures. Our first example is unmixed gunpowder, which is the same stuff as before. Our second example is oxygen bubbles unevenly dispersed in water after hydrogen peroxide decomposed into water and oxygen. Our final example is liquid bismuth and its impurities, which float to the surface because they are less dense than liquid bismuth.
All 3 mixtures are heterogeneous mixtures because they are unevenly dispersed, not uniform, and you can pick each of the components out individually.
Okay, this is a last minute addition we forgot about. All the elements that we've mentioned, they're all elements because they can't be divided further without losing the properties that mark them as those unique elements.
All of our compounds are compounds because they are all combinations of elements in set whole number ratios.
And our mixtures are mixtures because they don't have set ratios and can still exist in ratios besides the ones we've already described. I don't know why we filmed the outro and the intro this late. It's really dark. You can barely even see us. But anyway, that's the end of the video. I think we met all the requirements. We spent way too much time on this.
Yeah, but before we let you go, here's the blooper reel.
Oh no!
It lit the watch out. Yeah, I guess that's
Wait, the back.
be careful actually that it it's gonna crack the glass. So just be careful in case it cracks. But that's a good reason to move flammable substances away from such as gunpowder away from burning things. Yeah.
Oh!
You got some hydrogen there. Yeah, that was an interesting result.
Yeah, nothing's happening.
This is kind of disappointing.